Welcome to the chat. Welcome to the live. I've got this little spoon set up here. We're going to get right into it. We are going to get right into it. Here we go. It's liquid nitrogen month, of course, on the Tommy Technetium channel. And I'm going to pour, this is just a live version of the short I put out on Saturday morning. I'm going to pour a little liquid nitrogen in the spoon. We're going to watch what happens. Oh, not quite enough. It's a little tough to get it in there. Give me a second here. There we go. I got quite a bit. Now, what's interesting is it's not boiling away immediately. That's because you can tell it's boiling, right? You can see the little bubbles that are happening there. Yeah? That's because the liquid nitrogen's boiling. Now, it doesn't boil away all immediately because it boils so fast. There's a vapor barrier that it's actually resting on. And that vapor barrier is insulating it from the spoon, and so it doesn't boil away quite so quickly. But you might notice if we kind of watch, it's really hard to see in fast motion. But do you see those lobes that are being generated there? There it is, man. There it is. That's a Leidenfrost star, we call it. So the effect where a liquid is placed on a surface that's much higher than its boiling point is called the Leidenfrost effect. Look at that star. Look at that little star that's just forming there. Come on, look at that. Wouldn't that be cool to be able to look in slow motion? I think we have 4 lobes. Let's add a little bit more. What's going on, Giga Bean? All right, let's add a little more. We're going to try this again. Oh, it's always hard to get a bit in there. Hold on. Let me see if I can pour some liquid nitrogen in here. Pouring liquid nitrogen into a spoon. There we go. It doesn't all boil away immediately because that spoon is really, really higher, much higher than the boiling temperature of liquid nitrogen. And so on the surface of the spoon that's in contact with the nitrogen, there's actually a vapor barrier there. And that vapor barrier is insulating the liquid nitrogen from the spoon. Now you also notice some bubbles. If we can get those, well, it's not if the bubbles start to pulse in a manner that's periodic, there will be some waves set up in the liquid nitrogen. And if the frequency of those pulses fits the frequency of a Leidenfrost star, we can actually see it happen. Let's see. There it goes. You can see some lobes growing. Quite a few, actually. I'm not real sure how many there are. It's hard to see in fast motion. You can see it a lot easier in slow-mo. There it goes. I call these Leidenfrost stars, and you can indeed see these. If you want to learn a little bit more about them, you can look at the short that I uploaded on Saturday. You can see the bubble pulse there. They're all blowing up. Oh, we didn't quite get this. So we got a nice 4-lobed star last time. Let me add a little bit more. That's liquid nitrogen you're looking at in a spoon. I'm going to pour a little bit more in, just a little bit more. There we go. And the nitrogen, as it boils, it makes bubbles. And if those bubbles start to pulse in a periodic manner, and if the frequency of those pulses matches the frequency of what I call a Leidenfrost star, we'll get some lobes formed there. Hope it works. There we go. So you can see that bubble. Come on, baby. Come on, baby. Give me some lobes. Give me some lobes. Looks like it's struggling to form. Come on now. There we go. You can start to see some formation. There we go. I wonder if there's a little bit of ice in there. Sometimes if you get some solid material in there, I think I might have some solid in there that's screwing it up. Let me try this again. Ooh, that's cold. Okay. There's our spoon. I'm going to try to get that set just right. We'll do this one more time. I have a whole bunch of different experiments ready for you today. This is just the first one. Now let me show you the lineup. Let me show you the lineup of experiments we're going to be doing today. We're going to be doing Leidenfrost stars, kick it off. Then we're going to play with some blue morpho butterfly wings and liquid nitrogen. Then we're going to play with some LEDs and liquid nitrogen. We're going to use a superconductor. And then maybe we'll do some balloon brittle experiments. So that's where we're headed. Let's get back to this Leidenfrost star experiment. Let me pour some liquid nitrogen into the spoon. See if I can get just enough in there to make a star. You can see I poured it in there. We're going to zoom in. Going to zoom in. I'm having trouble seeing the comments, folks. So I apologize for that. I'm try to make sure I can see them, but they don't seem to be coming through. So I apologize I can't see the comments at this point in time. Come on, baby. Show me the Leidenfrost star. This one I think is going to work. You can already see kind of the undulations around the outside, and you can see that bubble is centered pretty well. I think if we get to the right size, we're going to be good. Come on now. Yeah, I can see a little bit of undulation going on. There we go. I think we have a large lobed Leidenfrost star right there. Definitely have one. Those larger ones tend not to last quite as long. Let's zoom in just a little bit more. Yeah, they're hard to catch. They are hard to catch. It took me a long time. Oh, it looks like it wants to do a 3-lobe. It's 2-lobed right now. 2-lobed star. Very cool, huh? Very cool. Yep, there we got a 2-lobed star. I'm sorry, Windexian. Maybe that's the issue. Maybe the issue is that there's a lot of ads popping up. Look at that. You can see a little 2-lobed star. We're going to try this one more time. Come on now. I want you to see this. If you want to see a good one, you can certainly watch the YouTube short that I uploaded this Saturday morning. That might be the issue, is the ads. So in Normandy, what I'm doing is I have placed some liquid nitrogen into a spoon. The liquid nitrogen is boiling. It's not boiling very fast because of the Leidenfrost effect. What that is the nitrogen boils very rapidly, and that forms a vapor barrier underneath the droplet. And the liquid is riding on that vapor barrier, and it insulates it from the spoon, and so the liquid nitrogen doesn't boil away immediately. Now, you can tell that the liquid nitrogen is boiling. You can see some bubbles that are going to occur every now and then. If the pulses of those bubbles match a certain frequency, the frequency of what we call a Leidenfrost star, you can start to see lobes start to develop, which I'm starting to see right now. Each star has its own particular frequency. That depends on how big the droplet is. It depends on the density and the surface tension of the droplet, things like that. But you can already see right now we have some lobes developing. We also have a little ice crystal in there that's floating around. You see it? It's kind of like bumping into each of the lobes as it goes. And those ice crystals, unfortunately, do disrupt. They do disrupt the star formation. I'm hoping you guys get to see look at that. You can see the pulse there from the bubble in the middle. Yeah, I think that ice crystal's messing us up. If you want to see some very interesting Leidenfrost stars that I was able to capture, you can always look at the YouTube short that I uploaded, my most recent one. But this isn't working as well as I'd like, so you know what we're going to do? We're going to move on to the next experiment, which is dealing with blue morpho butterfly wings. This is Liquid Nitrogen Month on my channel, so I'm going to do a lot of different experiments using liquid nitrogen, and now we're going to move on to doing some experiments with blue morpho butterfly wings. Thank you, Johnny Z. I appreciate that. Please remember to like and subscribe. That'd be very helpful. Here, let's look at this. This is a blue morpho butterfly wing. I do not kill the blue morpho butterflies. I buy them from the butterfly company, and they assure us that they do not kill the butterflies. They just harvest them from South America, where a lot of them are already dead. And what we're going to do is we're going to pour some liquid nitrogen onto these blue morpho butterfly wings. Now let's leave one of them out for a control. All right, so I'm going to leave this one out here as a control. We'll just stick it right there so we can see that color. And what we're going to do is we're going to place some liquid nitrogen in the other one. Let's see what happens. Come on, baby. Look at that. Come on, baby. Look at that color change, huh? You see that color shift? Here, let me get this. See like a color shift to a greenish? What the heck is going on there? And why does liquid nitrogen have something to do with that, right? Why that color shift to a green? Watch what happens. Look at that. Watch what happens as the nitrogen evaporates away. I think I might be able to get the lighting just a little bit better so you can see that color pop. The green is really beautiful. If I can get it to pop. Hold on just a sec. We'll get this light in here so we can see that there's definitely a color shift. It's more aqua now than it was before. Yeah. Now it's looking blue. There we go. There we go. Pop it in there. You see the shift to green. Well, you can see it. I dripped a little bit down there on this one here. Actually, the lighting is good here. Let me pour it on this wing here. I think the lighting's good enough to capture it. Look at that. See it? You can see right where I poured it, that green color. That beautiful green color. So beautiful. Let's zoom in on that so you can see it just a little bit better. I hope that doesn't change the angle, which is going to change the... Here we go. In goes the liquid nitrogen. Oh, look at that color shift. Huh? Look at that. And you can even see you can kind of see it's like got a ridges in there. You can definitely see the ridges. So what the heck is going on here? What is this? Well, what's happening in this particular experiment? Yeah, let me show you here. I'll pull out this paper. You can check it out. Here's just a paper here, okay? It does look like a fingerprint. And here's a really strong microscope view of these blue morpho butterfly wings. Let me pour a little more liquid nitrogen on there so you can see it. There it goes. Look at that. Look at that color shift. Huh? So here's a see this? This is a paper that has microscopic images of these little protein structures that are present in our blue morpho butterfly wing. And what happens in the blue morpho butterfly wing is it interacts with light in a way that makes it so that blue light ends up interfering with each other. The blue light interferes with each other and all the other colors cancel out. And so it's the blue light, because it's interfering, and constructive interfering, I should say, that's the light that gets directed toward your eye. Whereas, on the other hand, all the other colors of light are just, canceled out, basically. And the color of light that ends up getting, focused into your eye depends on, let's look at these structures again. It depends on the distance between these little tiny ridges they call these lamellae, these little tiny ridges in the lamellae, and what's inside these lamellae structures. So it's normally air. So it's normally air in here. And, because of the sizes of these gaps, these tiny gaps, and the air that's in here, that makes the light interact with the wing in such a way that it's blue that gets reflected. But when we pour liquid nitrogen on there, it displaces the air in between. It displaces the air in between, fills it with liquid nitrogen, and that changes the way the wing interacts with light, and so it changes it to green light rather than blue that gets constructively interfered with and focused toward your eye, toward the camera in this case. Isn't that beautiful? Looks like a fingerprint. Thank you there, Bart Batul. I appreciate that. Very much appreciate that. But yeah, and what's cool about this, you can even see the liquid nitrogen evaporate away. Yeah, give me a double tap, like and subscribe. Appreciate that, Yeka. Appreciate that. Do other gases change it to other colors? You know what, Carmen? I have not had the opportunity. The issue is you have to liquefy the gases. So I've got to liquefy the gases and pour them into the wings. But what we can see is we can put other liquids other than liquid nitrogen in there. Hello there, Charlie. We can put liquids other than liquid nitrogen onto the wing and see its effect if you'd like to do that. So let's try that. We'll go ahead and I'm going to move this wing out of the way. All right, and I'm going to pop this wing right there on our plate so we can take a look at this. And we're going to try, thank you there, Cameron. We're going to try it. We're going to look at it. So first I'll do water. So I just got a little bit of water here. We're going to drop a few drops of water. You can see it just dribbles right off. Now the reason for that is because, remember, that wing has a lot of nooks and crannies in it. And that means in order for the water to fill those gaps in between all those nooks and crannies, the water has to spread out. But water has a very high surface tension. Surface tension is a measure of how easy it is for a substance to spread, a liquid to spread out. So water doesn't spread out very well, so it can't fill the nooks and crannies. But if we try, let's try alcohol. I'm going to try some alcohol instead of water. We'll give that a shot. All right, here we go, alcohol. And then we got to get back to the liquid nitrogen experiments because it is liquid nitrogen month on my channel. But anyway, here we go. We're going to do alcohol, which has a low surface tension, and look at that. The alcohol wets the wing. And in addition to wetting it, we can see it also changes that color. Look at that, to that green. So we see that in addition to liquid nitrogen changing the color, in this case, it changes it kind of to a forest green. So the alcohol has a low enough surface tension that it can fill those nooks and crannies I was talking about in those protein structures. And as it displaces the air, it's going to change the way the wing interacts with light, and we get a color shift from blue to green. I'm gonna blow on the wing now to try to get the alcohol to evaporate off. Here we go. That takes a while. Maybe an emerald green, Johnny. I'll buy that. Oh, that's cool, Zur. So the wings get discolored if I want to. Oh, that's cool. So Zur sells insects, which is cool. Do you sell these blue morpho butterfly wings? The first drop made a perfect face. Zero. I guess it's Zero Cool Ninja. Do you sell blue morpho wings? Because I can always find a new supplier. Look at that. It takes longer, obviously, for the alcohol to evaporate. Let me lift it up off the. There we go. I'm going to lift it up off the surface. That should make it evaporate a little more quickly. There we go. I'm going to blow on it, try to get the alcohol to evaporate. Oh, it's taking a while. It's taking a while. Flap, flap. Yeah, let's just put it over here. You know, something I've wondered is like, what would happen if I pour some liquid nitrogen onto this while the alcohol is in there? So will it change color if the alcohol freezes? We're going to find out. We are totally going to find out right now. I doubt it, but you never know. That's why you do the experiment. I don't know. What do you think? It's hard to tell. I didn't have a control nearby. Yeah, it's 91% isopropyl that I'm using. Any idea if the structures on the wing are at all related to the ones on peacock feathers? I do not know. What I do know is I've tried this experiment using blue jay wings, and it doesn't work with blue jay wings. So my sense is no, but I can't claim that with a with 100% certainty. It's more like 1%. Somebody can look that up for us for Camero. That'd be welcomed. My senses, my hunches is it's different, but I really don't know. Okay, so we've done our first two experiments with liquid nitrogen. Let's look at the next one we're going to do. What's the next one on the list? Let me see here what I got. Oh, we're going to do the LEDs. Let's do the LEDs next. This is going to be fun. Hello there, hello there. And any of these that you all want to continue doing, certainly let me know. We don't have to just do the ones on the list. I want to keep it moving. I want to do a bunch of different experiments for you today. It's liquid nitrogen month on my channel. So if you want to see liquid nitrogen experiments, you may certainly, like, subscribe. All right, let's pour a little liquid nitrogen in here. we're going to try looking at some LEDs, okay? Light emitting diodes. Thanks, sir. iFanstar, appreciate that. Hello there, baby. Welcome aboard. So what are we doing next? I'm going to take some LEDs. Let's take a yellow one, all right? We'll turn out the lights. This is going to be cool. Okay. Let's do a yellow LED. I wonder if we'll be able to see it. I guess we'll find out. If I have to turn off the lights, we'll figure it out. So here we go. I got my yellow LED here. Let's get it going. Yep, I got it going the right way, all right? Ah! It's a little tough to do. There we go. Oh, wrong way. All right, I got my yellow LED, yeah? That's my control. We'll stick that down there. That's at room temperature. I think this might look better in the dark. All right, there's my yellow LED. Here's another yellow LED, yeah? Same colors, more or less. What I'm all gonna do, yep, light emitting diodes, and I'm going to cool this one in liquid nitrogen. So in it goes. We're gonna dip it down in there, and we're gonna watch what happens. Come on, baby, there it goes, there it goes. Come on, man. Isn't that crazy? It changed to green. Isn't that beautiful? Isn't that crazy? So what the heck is going on here? Well, a light emitting diode works based on what's called a band gap. So there's an energy gap. Here, I'll stick those down there. It's much easier to see here. Here's your control. Ah! Two definite different colors, yeah? This one's more orange. This one is definitely green. So there's something called a band gap. And it's just a difference in energy between what we call the valence band, the high energy band, and the conduction band in an LED. And when you chill the LED in liquid nitrogen, the conduction band, the atoms in the conduction band, they get closer together, and that lowers their energy. And because the light given off depends on the energy gap, if you lower that energy, it's gonna change the color. That's all. That's all that's happening here. Isn't that beautiful? Come on, baby. It's like a yellow-green. You want to try another color? If you want to try another color, I tell you what. I have, what do I got? I got red, I got green, and I got blue in addition to yellow. If you want to try another color, put the emoji heart in the chat of the color you'd like to see me test. Whichever one I see more of, that's the one that we're going to test. Right now, we changed a yellow LED into a green LED. Yeah, it went from yellow, and this one's green. I see a blue, I see a red, I see a blue. I see a blue, I see another blue. Okay, I'm seeing more blue than anything else. That's what we're gonna test. I have no idea if this is gonna work or not, but we're just gonna try it. That's what we do around here. We just try crap, all right? FAFO, right? All right, here we go. Let me get a blue LED. We gotta get our control going. So here's, this one will be the control this time. All right, there's the blue one going. I'll turn that light out there in the back in a second. I'm just turning it on right now so I can see what the heck I'm doing. All right, here's this blue LED. Let's get those lights turned off, and let's see if we see any effect from putting our LED into the liquid nitrogen. All right, here we go, baby. Let's see. In it goes, in goes the blue LED. I am Wendy. I am a PhD scientist. I got my PhD at the University of Michigan. Long time ago. I taught middle school before that. I don't know if that's a color shift. I think it is. I think that's a little more violet. What do you think, huh? You see it? Can you see it's kind of like a little more of a violet color? And that would be expected. Violet is a higher energy photon than a blue one. I think we got a little shift. You give me a thumbs up in the comment if you think that looks a little more violet. You give me a thumbs down if you think I'm full of crap. That's okay. You can disagree with me. I do too there, Bumblebee. Looks like Josh thinks maybe it's a little bit of a shift. Josh giving me the thumbs up. Anthony saw it. The Concept of Ash saw it. Cameron saw it. Cameron Tyrell. Yeah, slight color change. I saw some people ask for red. Let's do red next, okay? Show what happens if you reverse the polarity of the LED. Sure, let me get the lights back on so we can see this, okay? Hold on. So your LEDs only work. They only work if you set up the polarity right. So if you look, you know, I've got the positive end of the battery here, the negative end of the battery here. And what you do, if you look at the LED, you can see that one of the ends is longer than the other. You have to set that one up on the positive, like that. If I flip the battery so that the polarity is reversed, nothing happens there. Nothing happens there. Your LED is not going to light unless the polarity is properly aligned. Hot Wheels says not much, but says it's a bit. Minrad wants to go red, so that's what I'm doing. Here we go. Let's try red. Let's get our control going. You know why I started with yellow, don't you? Because yellow always works very, very well. If I remember correctly, I think I've done red before, and I think it works fairly well. So here we go. I'm going to get my control going. Let's make sure I got the polarity right. I do. So there's my red control. We're going to pop this down here. What does PFP mean? You have to forgive me. I don't know. I don't understand I don't know what that means. All right, there's the other one. This is the one that's going in the liquid nitrogen. Let me get the lights out. So why does it happen, John? So why does it happen is here. The color that an LED gives off depends on something we call the band gap. The LED is made of materials that they have what's called a conduction band. The electrons, that's where the electrons exist in the conduction band. Then there's a higher band up that's the valence band. My apologies. The electrons are in the valence band of the LED. Then a little higher up, we call that the conduction band. And what basically happens is you want to get some electrons promoted from the valence band to the conduction band, to a higher energy. And then what happens is the electrons that are up here, they drop down. And when they drop down, they give off light. Now here's the deal. The color that they give off, thanks there, Alec, I appreciate that. The color that they give off depends on the difference in energy between the conduction band and the valence band, okay? The wavelength, the color, all of that, yeah? So what happens when you cool an LED in liquid nitrogen is the atoms in the LED get closer together, and that lowers the energy of the valence band. And if you lower the energy of that valence band, you're going to change the energy gap, and that's going to be a bigger energy. Bigger energies shift to bluer, shorter wavelengths. So usually when I dip these in here, you're going to see, like, you know, your reds, orange, and yellows. Those are going to shift to greens, blues, and violets. Everything's going to get more blue. Okay, let me try these two. Lights out so we can see any difference. All right, here we go. Hey, thanks there, John. Thanks for the question. Glad to hear we got people on from Germany. Here we go. We're going to put this red LED in some liquid nitrogen because it's liquid nitrogen month on my channel here. All of December. Here we go. Let's dip that in there. And it goes. Now, a longer wavelength photon than red is orange. And the fact that I see it's not working quite as well, but I can definitely see that looks a little bit more orange than it did before. Absolutely. That definitely looks orange to my eye. It's a little hard to see. This one went out. There's a control. Let me try to hold them up side by side. Come on, man. There we go. Hey, pull them back a little bit. Yeah, that's a little hard to see. It's so bright. Let me try it with the light on. This might be too much light. Let me cool this one down just a bit. Boy, that is really hard to see, folks. I can see it with my eyes, and even here, it's really hard to see. Yeah, this one is so cold that it's barely lit up. I apologize. I can see it with my eyeballs that this one looks more orange and this one looks more red, but it is difficult to see on the camera. There it is. There it is. I caught it. You see how this one looks more orange at this point? I can see it with my eyes. I can see it on the camera right now. This is definitely looking more orange and this one looks more red. Hello there, RR. Glad you saw it too, Hot Wheels. Video Gamer says it's fake. You know what's nice about science, Video Gamer? You don't got to believe me. Do the experiment for yourself. I look forward to hearing your results. All right, here we go. Let's show, let's see if this, let's try it with yellow. Yellow, you can really see the difference. Yellow is very easy to see. How do you do this? You just get some LEDs, you get a button battery, you get the LEDs glowing, and you drip it down into some liquid nitrogen. All right, here you go. Here we go. I got 2 LEDs, both of them yellow. All right, we're gonna dip one in the liquid nitrogen. You can see it starts out yellow, and as it cools, you can see a shift to green. Something about empirical evidence, Video Gamer. You just can't argue with it. Look at that shift to green. Come on, man. Video Gamer's green with envy. Here we go. Isn't that cool, the garlic? Thanks there, Hot Wheels. It's physics, baby. So, Brazy, what I'm doing is I'm taking a yellow LED. I'm dipping it down into some liquid nitrogen really carefully. Lexington, I am dipping some LEDs down into liquid nitrogen, and you can see it shift to a green color. Oh, we got someone who's green colorblind and can see the shift. Woo! That's cool. Isn't that beautiful? What a beautiful color shift to green. By the way, I'm doing experiments with liquid nitrogen on my channel right now. It's liquid nitrogen month on my channel. If you like that kind of thing, you might want to like and subscribe. You will see a bunch of liquid nitrogen experiments. I post a new short every Saturday. It is a beautiful green. Does it change? Yes, it does, Lexington. It's going to change back when it heats up here. I'll try to warm it real quick with my fingers. Try to get it warmer. Okay. See, it's a lot more yellow. Yep. We'll dip it back down in. There we go. Oh, man. It's getting a little cold for me to hold. Just a bit. I'm not dipping my finger in there, but it's cold. They all change, but the yellow one is most dramatic there, Wake Up. If I drink it, I won't just become green. I probably won't make it. No, this is not how RGB lights change color. Isn't that cool? So yeah, as it cools, it changes to a green color, and then I'm going to warm it up. We'll warm it up. Thanks, man. I appreciate that, CL. Thank you for the subscription. I appreciate that. Do I have a purple one? I don't, but we did test blue. No, Petri, I'm not drinking it. There was a woman who drank some liquid nitrogen in England, and I believe she died in London. They gave it as part of a drink, and yeah, she either died or she had major damage to her digestive system. All right, maybe have you had enough? You want to try another color? I don't know. You want to see the blue one? All right, some people want to see the blue one. Let's do it again. Here we go. Put LEDs on both sides of the cup to show the difference, says YD Ozark. Yeah, we'll try that, YD. I agree there, Lexington. All right, some people want to do the blue one. It does look delicious. I agree with you, but yeah, it's not, you know, lots of things look delicious, eh? I shouldn't be drunk. Here we go. Let me just get this light on so I can see what I'm doing here for a second. People want to see the blue one. The blue one is subtle. I'm just going to warn you ahead of time, okay? I do have green. We'll do that next, okay? So, Wendy, I don't remember where you left off, but we've been just continuing to put LEDs into liquid nitrogen. Here's a blue one. Yep, there's a blue one. There's another blue one. There it was. Thank you, John. I appreciate looking that up for me. Yeah, we can do a red one, Magic. You got it. I don't have pink. All right, Petunia, we're going to do it. We're going to do blue right now. Let me turn this away so we can see things a little bit better. All right. All right. Does liquid nitrogen make the styrofoam brittle? It does not, interestingly enough. Okay, here we go. We're doing blue. All right. So in goes this blue one into the liquid nitrogen. You might see a shift to a little bit more violet color, just a bit. You see it? Slightly more violet, and it's easier to see if I leave it in the liquid nitrogen or above the container. You can see it's tough to get the lighting right. I can see it with my eyes. I'm trying to get the effect with the, on camera. It's a little tougher. Holy cow, super duper. Appreciate you looking that up. Thank you there, Petunia. Once again, explain why it happens. It happens because LEDs have, they're made of materials that have what we call all right, it's lesson time. Real quick, so we get back to the experiments. LEDs have something that we call a band gap, and the band gap is like this. So we have what's called the valence band in an LED, and this is energy. This is increasing energy, okay? And then we have what's called the conduction band. And the valence band's got a lot of electrons in it. We like to draw those with arrows like this, okay? And there's a few electrons up here in the conduction band. Yep. So that's what happens when you apply the battery to the LED. It's going to promote some of these electrons to the conduction band, okay? Now these things don't stay up here forever. They drop back down. And when they do, they lose energy, but they give off that energy as good old light. And here's the cool thing. The color of the light given off depends on this energy gap. And what happens when you chill it in liquid nitrogen, the atoms in the material get closer together, and that drops the energy of the valence band to a lower energy. And if you do that, these things drop a longer way, and so they give off a different color. And that color is going to have a shorter wavelength, but a bluer color. Shorter wavelength, higher energy. That's it. All right, let's get back to doing experiments. Thanks for listening to the theory. A lot of people like that stuff, but not everybody does. Some people just want to see what's going on. So let's do green. We haven't done green yet, so that's next. Green is next. I don't remember what happens with green. I'm going to fill this with a little bit more. Oh, you have to forgive me. I got to get a little more liquid nitrogen. Just a bit more. We'll fill this up. We're going to try it again. Okay. Fill this up. So it's a little easier on my hand. There we go. All right. We can do red next there, Magic Stars. We've done red before, but we'll do it again. Unless you guys want to get to the other experiments that we've got. I can show you my superconductor if you wish. We can certainly do some superconductor experiments. So what we're doing, green? Green it is. What happens if you put the LED in alcohol? Oh, we could try that, Johnny. We could try that. How cold is that room? The room's room temperature. Like 20 Celsius, 25 Celsius. You're welcome, Magic Stars. Here's the green one. So H. John, what we're doing is we are putting some LEDs into liquid nitrogen. All right? Thanks, Sir Lexington. Okay. All right, here we go. I'm going to turn this around so that we can see the experiment a little better. Down here's the control. That looks green to my eye. In goes this. I don't know what's going to happen. Let's see. Lucifer, probably if we used a violet LED. Yeah, that green shift. It is cool to see kind of the condensed water vapor. I'm not seeing a color shift in the green. Now, the green could be made by a material that I don't really understand what's going on. That happens sometimes with LEDs. You'll have to forgive me. But to my eye, those look the same color. And in fact, if anything, this one looks more yellow to me, which is backwards. I would expect it to look more blue, but in this case, for some reason, it looks like the energy gap to my eye, you can see how that looks a little more yellow, right? This in here looks a bit more yellow. That, well, maybe it looks the same. There's the first one. There's that. Yeah, I think those are the same color. I think there's no shift in the green. No shift in the green, man. No shift in the green. Probably more cold, Malto, but you could certainly try. Kim Jong, what we're doing today is we're putting LEDs in liquid nitrogen. We're doing a lot of experiments with liquid nitrogen. Thank you there, Petunia. I appreciate that. I agree, H. John. It didn't look more green to me either. Yeah, it needs to get really cold. Very cold. Let's do the superconductor next. What do you guys think? Give me a thumbs up if you want to do that. Give me a thumbs down if you'd rather see me put a different LED color in. What do you think? Superconductor says 2-time. John says yes. Someone says res. I think JD is saying come on to the superconductor. Yep, we're getting a lot of thumbs up. We got a thumbs down. I see that. David, lots of thumbs up. Okay, we're going to the superconductor. That's what we're heading to next. All right, let me clear my LEDs off. Boy, I got some mess to clean up here when we're done. I can turn the lights on for this. There it is. So this is a strong magnet. Let me get the lights on. Very strong magnet. All right. Let me turn off this light. Let me pull out my superconductor. It's a type 2 superconductor. And this is at room temperature, so I'm just going to stick it on there, on my type 2 superconductors here. And nothing interesting is going on at room temperature, okay? There's just nothing happening. There's just nothing going on, okay? But what I'm going to do is I'm going to chill these to below what's called their critical temperature. Their critical temperature is in kelvins, because that's what temperatures use. In kelvins, a superconductor's critical temperature is 92 Kelvin, but liquid nitrogen's temperature is 77 Kelvin. If you want Fahrenheit, that's negative 321 Fahrenheit, and these need to be chilled to about negative 290. So this is more than cold enough to chill our superconductor to a low enough temperature to get them to behave with magnets in an interesting way. 2-time, I usually stream around this time on Sundays. Usually once a week around this time. So it's at, what is it? It'll start usually at 3 p.m. Eastern time on Sunday. Usually. Not always, but usually. Okay, Celsius would be negative 196 for this, and about negative 180 for the critical temperature of the superconductors. So, let me get a glove on. I gotta get a glove on to do this. All right. I'm going to pull out one of the superconductors and we're going to get it on the magnet. We're going to see what happens. Here we go. Just stick it right there. What is happening? What is even happening? Look at that, baby. Come on now. Look at that. It is locked. It is quantum locked in place. Yeah? Look at that. It is hovering over the magnet. Yeah? Here, we can even turn it upside down, and it stays locked in place. Oh! There we go. Upside down, still locked in place. The superconductor is quantum locked in place. Maybe we'll even change the orientation a little bit, change it like that. You can see that it is indeed hovering above, and if I rotate it, below the magnet in the same orientation. There is space in there, you can see it. So the magnetic field cannot penetrate a superconductor. That's called the Meissner effect. Cannot penetrate. Yeah? So the thing is, though, this is a type 2 superconductor, and a type 2 superconductor has impurities embedded into it, and the magnetic field can penetrate the impurities. So there's magnetic field lines that you can imagine that are going through this superconductor at the impurities. And that's the only place they can go through. Now, if I try to nudge this out of place, it doesn't do it. It won't do it, because to do so, the field lines would have to go through the superconductor rather than through the impurities. And so because of this fact, the superconductor stays locked in three-dimensional space. It is definitely cool. This whole channel is cool this month because it's liquid nitrogen month, of course. All December. You think it's cold outside, why don't you come inside where it's liquid nitrogen month? Why does the temperature make a difference? Well, there's a lot of things that have properties that change depending upon temperature. What happens at the colder temperature is electrons in the substance, they start to pair up and send something that we call Cooper pairs. And when that happens, it ends up giving the superconductor its interesting magnetic properties. How you doing? Let's put it on this. What's nice is this thing here around an axis, the magnetic field seems to be constant to the superconductor. And so it can actually rotate around our ring here. So I'm going to pop this over here. Well, that's probably a little too warm. It's losing its property, so let me get another one out. And we'll stick it on the ring. We'll do this one here. There we go. Pop it on here. And we're going to give that a little spin. Isn't that cool? Quick question. Since you're teaching physics, I need help. If the body is a liquid, how does it turn into a gas? So yeah, if a liquid needs to turn into a gas, its molecules need to gain kinetic energy, right? There we go. Our superconductor is both floating and rotating on that magnetic axis. Very cool. If you want to see, I do have a long form video about quantum locking and superconductors. So if you want a more in-depth explanation, you can certainly, check out my long form video on that. I am Petunia. And we pop it over here. We put it on this side. Here, the magnetic field stays constant, and it does not want to get budged. We can turn that baby upside down, and it stays quantum locked in three-dimensional space. Come on, baby. Thank you there, Nicole. I appreciate it. I can use all the subscribers I can get. I've been having a rough time on my channel lately. I don't know what's going on. Can we make car suspension using physics? I'm sure people are trying, right? If we can get this to work at room temperature, are you kidding me? Wouldn't that be cool, huh? Wouldn't that be cool? All right. Let's do a real simple experiment, shall we? Just a real simple experiment. We'll just do Charles's law. Charles's law deals with again, all these experiments we're just doing with liquid nitrogen. So Charles's law deals with the volume of a gas with temperature. So I've got a little gas here in my balloon, and we're going to take this balloon. You guys are going to love this. And we're going to, let's back it up. I'm going to put that balloon in some liquid nitrogen and see what happens, okay? In it goes. I'm going to push it down in there. The gas is cooling. And of course, as the gas cools, as Charles' law would tell us, oh, look at it. Look at it. It's going. It's shrinking. Of course it is, because the gas in there is getting really cold. It's not that the gas is escaping. It's still the same amount of gas in the balloon. It's just that it's cold. And of course, gases shrink as they cool. Now, it's not dangerous to inhale this particular gas. If it's all you're inhaling, yes. But you inhale nitrogen all the time. 78% of the air is nitrogen. So let's see what happens when we warm our balloon up. We'll do that simply by taking it out and sticking on this right here. Watch what happens as it warms. It might pop. Is it going to pop? I think it did. Yep, it popped. But you can see that it expanded a little bit. Thank you there, Mayo. I appreciate that. Yep, it popped. Bummer. Bummer. Can we add some nitrogen groups to toluene? I'm not a synthetic chemist. That's not going to happen on my channel. Not happening on my channel. How long have we been going? We're going about 50 minutes. I got 10 more minutes, and I'm going to flip the camera around and talk to you all. Let's go back to those LED experiments, yeah? Sound good? Go back to the LED experiments. You can see, by the way, notice on our cup, see that ice formation on there? So this has got liquid nitrogen in it, yeah? How about just letting you look at liquid nitrogen? It's kind of cool to see. Let's do that. Let's have you look at some. We're going to just pour some into this container here. All right, give me a second here. Let's just take a look at liquid nitrogen. We'll pop this on so it looks nice and pretty. Get a little light going. Turn that just like that. And we are going to pour some liquid nitrogen in there. Let you look at it up close. It's just boiling like any other substance would, right? If it's above its boiling point. I need to actually get this on an insulator. There we go. And it's boiling very rapidly right now because the beaker is very hot compared to the liquid nitrogen. It does look unreal, doesn't it? Let's fill it up a little more, okay? Yeah, you can see it's completely boiling. It'll continue to boil. All right, let's fill this baby up all the way to the top. There you go. Again, it's boiling very rapidly again because up here at the top, the beaker is very warm. That's putting a lot of energy into the liquid nitrogen, making it boil rapidly. What if we place a strong magnet into the liquid nitrogen for 30 seconds to take it out? I don't know, we can find out. Here. Where's my, there we go. Take my neodymium magnet I got right here. Let's see, does this attract a magnet? It does. So I got my neodymium magnet right here. We're going to stick it to this spoon. You can see it's clicking on there. Somebody asked what happens when we stick a really strong magnet in there. Let's see if it loses magnetism, all right? You can see it's attached. We'll pop it in. We're going to see what happens. Here we go. How you doing there, Dr. Hayes? Great question, Mayo. So when I say that the styrofoam or the beaker is very hot, what I mean is its temperature is extremely high compared to the boiling point of nitrogen. So just like if you put water on a surface that's well above the boiling point of the water, then the water will boil. The same thing's going on here with the liquid nitrogen, okay? That's what I mean by it's hot. It's hot and cold are relative, right? And it looks like it's still stuck. So it looks like the temperature of the liquid nitrogen did not affect our strong magnet's ability to attract this metal spoon. I'm doing all right. No, Dr. Hayes, somebody just asked what would happen if I stuck a strong magnet in the liquid nitrogen, which is what I did. Now, people aren't going to believe this. I'm going to show you this, okay? Watch this. I'm going to actually touch the liquid nitrogen, okay? Here we go. You see that? Don't blink. You'll miss it. I'm going to do it one more time. Ready? Here we go. In go my fingers. Woo! So why am I able to do that? I'm able to do that because of something called the Leidenfrost effect. I agree, borosilicate glass is crazy. The Leidenfrost effect. What the Leidenfrost effect is this effect that if a substance hits a surface like my finger, if a liquid hits a surface like my finger, that's way above the boiling temperature of the liquid boils so fast it forms a barrier of vapor around that hot surface. So it's like when I put my finger in, the liquid boils, it forms a vapor barrier. Hey, thanks for the gift there, Voice. I appreciate that very much. Very much appreciated. What's the question say? How was your Sprite, Tommy? I apologize, I don't understand the question. How was my Sprite? Oh, this is Sprite, maybe, I don't know. Anyway, when I put my finger in there, my finger is so much higher than the boiling point of liquid nitrogen that a vapor barrier forms around my finger, and that protects my finger. It insulates my finger from the cold liquid. So I don't even feel it. It doesn't feel wet. It just feels like a real cold pillow around my hand. We call this a Leidenfrost effect. Hello, Wolf. Hello from New Zealand. Splash some water on a hot pan, drop the skin around. Hey, let's see that. We can drop this liquid nitrogen on a surface that's hot compared to the boiling point of liquid nitrogen. We can watch what happens. Let me see if I can find a surface on which we can do that real quick. Let me see. Maybe. Well, we want to be able to capture it in something. I'm not sure what I have here. Hey, thanks there, Revo. I appreciate that a lot. Thank you there, Ken. I appreciate it. We got someone from Narnia. Come on, man. Yeah, I think this might work. This actually might work. So I'm going to use this. I'm going to use this black brick. We'll pop this on the black brick, and we'll see what happens here. All right. I might need to turn the. Yeah, we'll turn that light off. We'll focus on the black brick over here. Let me get my camera focused on it so we can see what I'm going on. I'm just going to pour some liquid nitrogen into the black brick, okay? Let me just get the camera up just a bit so we can see it a little bit better. You see what I'm doing? It's a brick that, it's not greatly painted, but it's just an old brick that I painted black. You got it, Sial. Here we go. Here we go. Let's pour some liquid nitrogen in there and let's watch what happens. And it goes. You can see these little beads forming. Yeah, they don't last forever, but they bead up and boil away. I'm actually surprised. Those are boiling away pretty quicker than I'd expect, like a lot quicker than I'd expect. I wonder if that's because it's probably because the brick is porous. I need to find something that's not quite so porous. I know what I'll use, if I can find it. If I can find it. Yep, there it is. I got my little metal dish. We'll put my little metal dish in here. There we go. Why do I just have a brick on standby? I'm in the lab right now. So I got a lot of stuff available to me right here. A lot of stuff I do experiments with. So here goes the liquid nitrogen. We're going to pour it into this little metal container, little dish. And there you see, there's a puddle, and that puddle is going to last a while. And that's because as it hits this hot, compared to the boiling point of nitrogen, as it hits this hot metal surface, it boils really fast. And underneath this liquid droplet, in contact with the metal, there's a gas barrier there. And that gas barrier insulates the liquid nitrogen from the surface. I don't have any mercury there, Biohazard. What the heck? Biohazard's asking me to play with mercury. I love it. No, I don't mess around with mercury. Can I mix it with water? I can. Let's do that. Let's mix it with some water, okay? It's kind of fun to see. We'll do that next. All right? So you can see it's taking a while to evaporate away. I think we might be forming a Leidenfrost star. That's a video that I just had come out this Saturday. A YouTube short. I made some Leidenfrost stars with liquid nitrogen. There it goes! There it goes! We got it! Come on, baby! You see that? Do you see it? It totally went to a Leidenfrost star. You see it's like 5 lobes right now? Come on, man! We got it! We totally got it. We were trying at the beginning of the live to get those, and it just wasn't working. And you folks who are here now, you got to see it. Did you see the lobes? Hey, put a star in the chat. Put a star emoji in the chat if you saw the Leidenfrost star. It didn't last long. It didn't last long, but it was there. And now we see just a little bit of ice crystals left over. Come on, baby. Let's try one more time, huh? I doubt it's going to work, but we're going to give it a shot anyway. We're going to try this one more time. All right, we got some people who saw the star. I love it. Here we go. Oh, did we get lucky? All right. Here we go. In goes the liquid nitrogen. If you want to learn more about the Leidenfrost star, including an equation that relates the number of lobes to the frequency, you can check out my my short video I put out on Saturday. Come on, H-Junk. I see you, Void. I see you, BJ. I see you, Khadid. I see all you. I see you there, Ron, Lucifer, Two-Time, Dewar, Kathleen, LaGarlic. Beautiful. Giga Chad, I love it. Kicktronic, Wolf, yep. It looks like we might get it again here. I'm seeing some lobes, but I also see some ice crystals in there, and those tend to screw things up. When I see, there it is! There it is! It was very transient, but I saw a star there for just a bit. I know, right, Robbie? I love the comment. Who knew there was sacred geometry in liquid nitrogen? Liquid nitrogen month on the channel, baby. We're having a great time in here. So Compass saw the star, Bus saw the star, Lagarlic saw the star. We got some ice crystals in there. Let's go ahead. Somebody asked to see what would happen if we mixed liquid nitrogen with some water. We're going to do that next. Give me a second. I'm filling a beaker with water right now. All right, here we go. There's my water. Let me get this set up. I did some work on this just this week. So what you're seeing now is some material that I filmed for a video. We're going to do it live right now, okay? So I'm going to pour some liquid nitrogen into this beaker of water, okay? That's all we're going to do. Just pour some liquid nitrogen right on this beaker of water. I'm going to turn this light on because it'll make everything look a little bit prettier. Yeah, that looks nice. That looks nice. Maybe a bit more water. Ah, I like it. Okay. Give me a second. I got to get a little bit more liquid nitrogen. We're going to pour it on the top. We're going to watch what happens, all right? Can you make nitrogen bubbles, and can I make it a lesson? Yeah, there's nitrogen bubbles happening in here. Yeah? As it boils. It's hard to see. Yeah, let's see if you can see it from this end. There's the nitrogen bubbles as it boils. There you go. It's that simple. And it's boiling. Very cool. Here we go. Let me fill this up just a bit with a little more liquid nitrogen. We're going to try it. Here we go. All right, baby. I'm going to just get the angle of this just a bit different, just a bit. We want to make it look nice. And then I'll tell you what, this is going to be the last experiment that I'm going to do today. And then we're going to, I'm going to flip the camera around. You're going to see an old man in his lab. If that's not something you want to see, this is your fair warning. You're going to see a 57-year-old man in their lab. And it's definitely not something that everyone wants to see, so it's coming. Okay, here we go. Good to hear it there, Patrick. I do not, Froggy. I wish I did. Here we go. I'm going to go ahead and pour in the liquid nitrogen into the water. Here we go. Now what you might notice some bulges down below, but you'll notice the liquid nitrogen floats on top of the water. That's because its density is less than that of water. You will notice, though, that some of the water gets pushed up on the sides and then it freezes. Beautiful, isn't it? But yeah, you can totally see the layer of liquid nitrogen floating on top of the water. You can even sort of see that Leidenfrost effect. So there's a vapor barrier there that continues to form. And that keeps all the nitrogen boiling away rapidly. Pour a little more in there, top it off. You have to forgive me, I have to continue to blow on this so you can see what's happening. Although I think we're getting a bunch of, we're definitely getting a bunch of ice on the top. Try to mix it. Will not yet. Well, the way you want to get it to work where it quote unquote explodes is you pour the water on the nitrogen, because when you do that, the water forms a seal over the top of the nitrogen and the nitrogen pushes out. This way it doesn't make an explosion. Beautiful, huh? Just beautiful. It's like we're on Titan. I love it, Robbie. You can hear the crackles of the ice forming. Yeah. You can see some of the ice formed around the side. Very cool, huh? Thank you there, SW. What happens if I seal the mixture? Yeah, that wouldn't be good. Then we're going to have exploding glass. I don't want to do that. Elixir cup. It looks like it. All right, folks. let's flip this around. Let's talk to you a little bit before I leave for the day. Let's see what folks are talking about. No, I'm not sealing it. Yeah, I told you it was liquid nitrogen month, right? So when you get to my age, low T can be a problem. If you know what I mean. This is testosterone, by the way, the chemical structure of testosterone. But with liquid nitrogen, low T is not a problem. Low temperature is not a problem. Hey, thanks there, Revis. That was fun. We had a good time, man. We had a real good time. Thanks for hanging out. We'll just talk for a little bit, and then I'm heading out. What happened if the water was boiling? That's a good question. Thanks, Zom. Yeah, if you like the shirt, you can pick one up. You know, on I don't know. I think there's a link in my channel or something like that. You're welcome, Cassie. Thanks for joining in. How do you boost low T? You go to the doctor. Hey, so long there, Mike. Thanks there, Lucifer. We had a good time. Thanks there, Nicole. That's fun. Thanks there, Dewar. Thanks there, two-time. I don't think I'm going to be able to get into the lab next time around, but we'll see. We'll see. Hey, thanks there, Monster Tooth. I'm glad to hear that. I'm glad to hear that. Yeah, check them out. The Wise. Most of my stuff is short form. People don't want to listen to me for much longer than a minute. So my shorts, they do well. My long form, not so much. What's one of the craziest experiments I've done? Rico, one thing that I did that, I don't know if it's crazy or not, but I wanted to see the effect of altitude on the Diet Coke and Mentos experiment. And so me and a buddy, we hiked up Pikes Peak, and we did Coke and Mentos experiment every 1,000 feet. We also did it, you know, we got below sea level in Death Valley. I went to the beach in North Carolina. I went to the highest point east of the Mississippi. I think that's Mount Mitchell in North Carolina. And we did Coke and Mentos experiment like all over the United States at different altitudes, and there's a clear effect. You know, as you get to higher altitudes, the atmospheric pressure isn't as high, and the experiment works better. And for one reason, is because, you know, gases expand at lower pressure. That's one reason, but that didn't explain all our results. There's also a kinetic effect, so how fast the reaction can take place also speeds up at increased altitude. That's some well-known physics and bubble formation. And yeah, it applies to those experiments as well. Hello there, Hello there, two-time. Thanks to Wise. I'm a little nervous to do that, Compass. Oh, thanks there, Monster Tooth. Not very well, Tom. I'm not a synthetic chemist. No, this is not a home setup. It is not a home. It is a fume hood behind me, yeah. Dewar, I felt like a really cold pillow of air around my finger is what I felt. There, we can check out. Here's the nitrogen has stopped boiling in our beaker, and boy, you can see quite a bit of ice in there. Quite a bit of ice in here. Yeah, that was a fun experiment. Thanks to who I forget who it was, but thanks to who suggested we do that experiment. Hey, I think I'm going to head out, folks. I definitely enjoyed doing the live with you all today. This is the first time I tried it in the lab. Had a good time doing that. Thanks for hanging out. And remember, take some time to look at the beauty that surrounds you. It's all over the place, man. It's everywhere. Take some time, breathe it in, look at those sunsets, check out the clouds, look at the way water flows and the way it sounds as it flows through a brook or something like that. And you know what? Take some time to understand the science, too. Because when you understand the science behind the beauty gets all the more beautiful. At least that's the way I see it. Thanks for hanging out, everybody, and we're going to see you next time. Had a great time with y'all. So long.